Hey guys, this is the third video, and these go with Unit 3, 2 quantitative variables. So the first question in this section is 17. It says, women who are overweight suffer from economic consequences as shown in this study. Their household income, so that's one quantitative variable, was less than 6,710. The findings were from an 8-year observational study, so that's important, of 10,000 randomly selected women in this age range. If there is a difference in the income, does it give this a convincing evidence that being severely overweight causes a woman to have lower income? So essentially, if you look on our Unit 2 notes, it specifically says under observational study, two variables have a correlation, but we cannot say causation, right? So our answer here is E. The study does suggest an association, but not cause and effect. We cannot get cause and effect unless it's a properly designed randomized experiment, right? Properly designed randomized experiment. Okay. 17 goes. The next one in this section that's kind of, and this isn't perfect, but it kind of falls in this, this one is perfectly fits in, but the other one maybe could have been in design as well. So it says questions 27, 28, and 29 all go with this information. So a park ranger measured the neck of 10 bears, that's tough to do, and took their weight, also difficult. And we created this formula. So if you don't know how to create this formula, I'll recreate it. Notice that this information here is what we need to create our prediction model. So y predicted is equal to the first number, plus, there's no negative sign there, so we see our slope is positive, times our neck girth. So we, if we know the neck girth, then we can predict the weight of the animal. So instead of a y, I'm going to write the word weight. Okay. Now there's some other information, and most of the time up until now, I told you ignore all this stuff over here, but that's the very last section, and I'm kind of teaching it through these videos. I'll also be teaching it a little bit in class, and you'll also see it on Statmatic. The other thing we might need, besides our prediction model, is to know R. How close are these dots on average to our line? And they look very close. So if R squared is 0.947, then R would be the square root of that. And we know that R has to be positive because our slope is positive, right? This is a positive line. So there is a strong positive linear relationship between neck girth and weight. As I said, it's strong because when I take the square root of 0.947, I get 0.973. So that is very strong. Any number even above 90 is going to be strong. So that's a very strong positive correlation between neck girth and weight. Okay. So let's see. Now let's tackle some of these questions. So it says, which of the following would be the correct value for the correlation? And the correlation is R. So as we said, to explain R, we know that there's because R is really high, we can say there's a strong, because this is a big high, positive, because the line was going up, right? The dots were going upward. Linear, nothing looked like a frowny face. Correlation between Y and X, whatever those variables were. So we notice which one matches our script, and we see that number 27D, the correlation is 0.973. The linear association is strong and positive. Beautiful. That matches our script from our notes. Now let's take a look at 28. It says, which of the following would represent a 95% confidence interval for slope of the population of the least squared regression line? So we haven't done this yet. It's the last section before you get to chi-squared, but we're kind of already reviewing, and then we'll just kind of learning about it a little bit at a time. All right, so we know that our formula is slope plus or minus, right, whatever our value is, test statistic, that's our statistic, our z star, but these are numbers, right? These are numbers or calculations, so it's going to be kind of this t value, right? And then your standard error of your test statistic. So what was your standard error of your test statistic? If you go back, see how the standard error of your slope, remember this is our slope. If I look back in my formula, that's the number in front of x. That's my slope. So this is the standard error of the slope, 1.695. Why did I, no, ignore that. Okay, so that is our standard error of the slope. That was me trying to see if they calculated by hand or not. So yeah, sorry, ignore that. So 1.695. So 1.695. And now I'm going to look for this t star value, and that's going to be in our table B. So let's take a look. Now our slope, we already saw that, right? Our slope was this number. It's always the number by the x, and this is always our x value, always, okay? So 20.23. So notice we can eliminate that. It's got to be 20.230 plus or minus. Okay. So now we need our formula sheet. So going to our formula sheet, AP Stats, I don't need table A, right? That's for z-scores. Table B says we're going to do a 95% confidence level. So see that on the bottom, but I can't use the infinity 1.96 because we only talked to 10 bears. So you might be thinking your degree of freedom is n minus 1, but remember we have two quantitative variables, so it's got to be n minus 2. So again, make sure you're on the right column for 95%. Scroll up to the 8 row, and I see the number 2.306. There's the number, 2.306. Okay, that's the number we need, 2.306. Okay, so 2.306 times 1.695, and I get this, which matches this, and I'm loving it. That's the answer I was looking for. Okay? So I know I didn't teach you this, but now I did, right? And this should make sense. So the idea is that as the slope or the change in y over the change of x, we don't know it exactly because we were just kind of approximating with our dots, but we know it's anywhere from about plus or minus 4. Yeah, so anywhere from 16-ish to 24-ish is the slope. So for every, right, so for every one, are these in inches, 1 inch of extra girth around the neck, you're going to have anywhere from 16 to 24 more pounds of weight. And do you see how this would be very useful for zoologists, any kind of people that work with the animals or in the park service. Now it says a bear was recently captured with a neck girth of 35, so neck X is 35 inches, and whose weight was in, so that's our Y, 466.35 pounds. If this bear were added to the data set, what would be the effect on X? Okay, so 35 and then 466, so 35. Oh boy. So these are counting by 5. I gotta move this. 46.35. That's actually looking pretty good. So let's look at our choices. Looks pretty much in line. I could have put it in the formula and seen how far off it was from your predicted. So you can plug this into your formula, plug the x in, and get a predicted y, and then you can compare it, right? And that's called a residual. But let's look at our choices. It says, we notice that by graphing it, this point lies on our least square regression line. So now we have to go to our notes and figure out what happens when a line lies on our least square regression line. We'll notice S is our standard deviation, how far off a number is. We know that S would go down, so we want to pick B. It'd be less varied. S would decrease because it landed on that line. So the numbers got less varied. Cool. All right, 38 falls in this type of question as well. So let's go up to 38. 38 says, which of the following is supported by these plots? So, okay, so, once again, we have a big, ugly number 38 and 39. Refer to the following situation. Do children's fears change over time? If so, how? So there was an initial rating and then a later rating, and they created a line of best fit. All right. Now, we haven't reviewed this, but you can actually get out your textbook and look. There is, instead of RNI, random, independent, and normal, to do what are the conditions that have to be met for a least squared regression line. And those spell liner, L-I-N-E-R. Okay, so I'm really just looking to see which one doesn't fall in line. So the first one is, it has to be linear, or you can't use a test statistic to find a least squared regression line. It has to be linear. We notice there's no frowning, right? No smiling. These dots are just kind of collecting up, if you will. So we are going to say this condition is met. We're okay. It's linear. Check a 10% condition. They didn't give us this, but I think it's safe to assume that if you talk to 94 people, you multiply that by 10, there's more than 900 some odd people that would fall in line. So this one's going to be met. Normal. Okay, if you look at this, it actually has to be normal for, remember you have two variables here, but what you should be looking at is, as you look across here, do the dots look pretty much clumped in the middle and spread out accordingly? So clumped at some midpoint. And everything looks, pretty much nothing weird exactly. So I'm going to say normal's fine. Now, an equal standard deviation, this says an equal standard, and this is right out of your book, an equal standard deviation of y for all values of x. So we're looking for the variability for low numbers and high numbers is the same. So our book actually gives you some examples where, what if the dots are really close together here on your low numbers of initial, and then they get more spread out toward the end? That would fail because that's not really an equal standard deviation. So if we look at our ratings here, it looks like they really only vary by a residual of about 0.2 the whole time. Pretty consistent deviations with a few numbers here and there, right? So that one's met. Was it a random sample? So yeah, this was taken randomly. So it looks like I've spelled out all of my conditions, L-I-N-E-R. All right, so I'm going to pick, there is no striking evidence that we can't do inference for regression. We should be pretty good to go. There's nothing glaring about this. Last question in this section, George's initial fear rating was 0.2 higher than Johnny's. So I made some lines here. I thought, let's say this is, if Johnny's had an initial rating of 1.8, they're essentially saying that George was higher. okay? Now, you can see that there's some amount of variability, but notice we do have a positive slope here. So it's safe to assume that, now, and again, you have a very low R, so this is not very data that you would be extremely dependable because R is so low, but we're going to use our slope. Remember, this is our slope. So our slope is the change in Y over the change in X. They told us that the slope is 0.398, right? And they said George's was higher. So I said the change of Y over the change in X. How did we know the change in X is 0.2? So George minus Johnny. We know George minus Johnny is 0.2. George is 0.2 higher. So we see here using the Lint swap, I can take the 0.2 and put it up here by the 0.398, that the change in Y, what would the model predict about their later fear ratings? The later fear rating is your Y. So 0.2 times 0.398 is 0.0796. That rounds to this one, so I've got my answer. George will be about 0.08 higher than Johnny. Thanks for checking out the video. Check the next one.